Imagine you are reading a long passage, maybe something complex, history or science. Your brain doesn't just process word one, then word two, and completely forget how the beginning connects to the end.
Exactly right. Your mind is, constantly mapping relationships. When you read something like "The black cat sat on the mat," you instantly know black describes cat.
Right.
That natural human thing deciding which parts are important to other parts, that's attention.
And that basic idea, it seems so simple, but that's the critical insight. The thing that launched, well, all the AI we use now, ChatGPT, Gemini.
It really is.
Yeah.
And look, the pace of new AI names, new tools, it can feel completely overwhelming if you're trying to keep up.
Yeah, it's a lot.
So our goal today is pretty simple. Let's get some foundational clarity. Think of this deep dive like understanding the scientific blueprints for these huge systems.
Okay, so we've looked at the source material, and it really boils down to four big shifts that made modern AI possible. First, building the core engine. That's attention. Then the scale needed for new powers, which is few-shot learning.
Getting bigger.
How we made them, helpful and safe alignment.
Crucial step.
And then how they actually connect and interact with the real world. That's RAG and agents. So let's unpack this. All right, let's start at the beginning. The cornerstone paper from 2017, the one that introduced the transformer architecture. Before this, AI had this, fundamental memory problem.
Huge structural problem.
Yeah.
Older AI models, things like recurrent neural networks or RNNs, they read text sequentially, like reading a scroll, word one, then word two.
Okay.
By the time they got to maybe the 50th word or the 100th, the computational memory, it just faded. They forgot the start of the sentence.
Meaning they couldn't realistically summarize a long document.
Yeah.
Or translate a complex paragraph accurately because they lost the context.
Exactly. They lost the context. The transformer totally changed this. It allowed the model to look at all the words in a sentence, basically simultaneously.
All at once.
All at once, which allows for massive parallel processing.
Yeah.
It can instantly connect the beginning of a really long sentence with the end. And the key mechanism is called self-attention.
Okay, explain self-attention again. You had a good analogy for this.
Right. Think about being at a noisy party. Okay. You're talking to your friend, but there are dozens of other conversations swirling around. Your brain uses self-attention to filter out all that noise and focus just on your friend's voice. The AI does basically the same thing. For every single word it processes, it gives every other word an important score. It builds this instantaneous map of relationships.
So instead of just step by step, it's building a whole web of connections for everything it sees. That sounds incredibly powerful. And it is, it's the foundation for pretty much every large language model today.
It is.
But you mentioned there's a big technical bottleneck baked into that architecture.
Yeah, there is. It's the quadratic resource limit. It sounds technical, but the idea is because the model has to calculate the relationship between every word and every single other word. If you double the length of the text you feed it, the computation cost doesn't just double, it squares. It grows exponentially faster.
Right, that term quadratic growth sounds academic, but when I paste a really long article into a chatbot and it slows way down, or maybe it just says too long, that's the quadratic limit hitting me.
Yes, that's exactly it. It limits how much text the models can handle at once, creating that context window. Okay, so the transformer could handle these complex connections. That ability led directly to the next major shift, just scaling things up.
Yeah.
In 2020, researchers showed that simply making these transformer models really, really big, think GPT-3, unlocked this completely new skill. It's called few-shot learning.
Few-shot learning. This feels like the moment AI stopped being just this, niche engineering thing and started becoming usable for, almost anyone.
Precisely. That's a great way to put it. Before this huge scaling push, if you wanted an AI to do a new task, like summarizing customer feedback in a specific way, you needed a team of engineers, probably months of GPU compute time, training it with thousands, maybe tens of thousands of examples.
But few-shot changed that. Why did just making the model bigger suddenly enable this?
Well, when the models got massive, they developed this thing called in-context learning. They weren't just predicting the next word anymore. They'd seen so many patterns in the training data that they actually learned to follow specific instructions given in, plain English. It completely shifted the paradigm from training a new model, which is an engineer's job, to simply writing a good prompt, which almost anyone can do.
You just needed one or two good examples in the prompt itself.
Yeah.
Show the model product, widget, price, and $10 once.
Yeah.
and it suddenly knows how to pull the price out of 1,000 other descriptions.
Yeah.
That democratization, that's really profound.
It is. It really is. But these early giant models,
Yeah.
they were still pretty flawed,
They're smart. Yeah.
but also incredibly stubborn sometimes. Excellent at predicting the next statistically likely word. But they didn't always grasp human intention. They could hallucinate very confidently or, give answers that were just wildly inappropriate or unhelpful.
Yeah, I still wrestle with prompt drift myself sometimes, trying to get the output just right. Even with the latest models, it's a real thing. So, this need for helpfulness brought us to the next key idea: alignment. Specifically, reinforcement learning from human feedback, or RLHF.
RLHF. This is basically the secret sauce that taught the AI to be a helpful assistant, not just a text generator.
Yeah.
They trained the AI based on what text humans actually preferred.
How does that work, like in practice?
It's basically a three-step process. First, you have human contractors actually write out high-quality, good answers to prompts. That's called supervised fine-tuning. Gives the model a baseline.
Okay, step one.
Step two, they train a separate, smaller model. Its only job is to predict which of two answers humans would prefer. This is the reward model.
Like a judge scoring the answers based on human taste.
Exactly, like a high score for helpfulness. Then the final step is the reinforcement learning part. They let the main AI generate answers. The reward model scores them instantly. And the AI adjusts its own parameters to try and maximize that reward score. It's like training a dog with treats, basically, reinforcing the good behavior.
And the big insight there was that a Smalley model that was aligned in StructGPT was actually preferred by users much more than the giant but unaligned GPT-3. Usefulness beat sheer size.
Yes, usefulness suddenly became the key metric. Alignment was critical.
So if alignment is so crucial and RLHF was the way, why are we seeing newer, maybe simpler methods starting to replace it now?
Well, RLHF is quite complex and, frankly, very expensive to implement. That's driving research into simpler, cheaper alignment methods like DPO. Okay, so we have this aligned AI brain. Now let's talk about connecting it to the real world.
All right.
First up is RAG, Retrieval Augmented Generation. This is essentially giving the AI an outside brain that can access current information.
Right, because we built this giant LLM brain, but its knowledge is frozen at the time it was trained. Why couldn't we just, retrain it more often to keep it updated?
Because retraining one of these massive models costs, potentially, tens of millions of dollars and can take weeks or months. It's just not feasible to do it constantly.
Right.
So its knowledge gets stale fast. Margay solves this. It works by first finding relevant external info, maybe real-time news, maybe private company documents. Then it adds that specific text directly into the prompt it sends to the AI.
Okay.
And crucially, it forces the AI to generate its answer based only on that source text provided in the prompt.
So if I ask my bank's chatbot about, say, my specific mortgage rate, which is private info.
Margay would search the bank's secure document database, find the paragraph with your rate, paste only that paragraph into the prompt for the LLM, and instruct it, answer the customer using only this text.
Got it. So the main LLM never actually gets trained on or learns my private data. It just uses it for that one answer.
Exactly. That protects privacy, and it also massively reduces hallucinations because the AI is grounded in a specific source document.
Makes sense. What's the main risk, then, when you're relying on a RAG system?
Well, the final answer quality depends entirely on that first step, the retrieval or search step. If the search pulls up bad or irrelevant info, the AI's answer will be bad too. Garbage in, garbage out.
Okay. That brings us to the next step. Agents. This feels like a really big shift, moving from the AI being a passive chatbot waiting for me to type something to being an active tool that can actually go out and do things to achieve a goal.
That's exactly it. Agents are about planning, using tools like running a web search, executing code, calling an external API like weather or stocks, and then, importantly, observing the results and correcting mistakes.
So what's the structure? How does an agent work?
It's pretty simple conceptually.
Yeah.
You have a brain, which is usually the LLM doing the high-level thinking and planning. You have perception, which is the agent seeing the results of the tools it uses, and action, which is actually using those tools. And it works in this loop. Think, act, see the result, think again based on the result, over and over until the goal is met.
So instead of me asking like 3 separate questions, what's the weather in Hanoi? What's the weather in Ho Chi Minh City? Okay, based on that, what should I pack?
Right.
I could just give the agent one complex goal, like compare the weather forecast for Hanoi and HCMC for the next 3 days and suggest what clothes I should pack for a business trip.
Exactly that. You give it the complex goal. Analyze the last 3 financial reports for Company X, check recent market sentiment about them on Twitter, and draft me a summary email recommending whether I should buy or sell the stock. The agent figures out the steps and uses its tools sequentially.
Whoa. Okay, imagine scaling that agent structure up to manage, say, 1 billion dynamic calendar scheduling requests a day across a huge company. That changes everything about how work gets done, almost instantly.
That's the potential, absolutely. It's the immediate future of productivity enhancement.
Yeah.
But these systems are still pretty new and can be tricky to manage reliably.
Right, they are complex. So what's the biggest, operational headache or risk when people try to deploy agents in the real world today?
They can still get stuck sometimes.
Yeah.
They might get into self-repeating loops, like endlessly searching for a file that doesn't exist or calling a broken tool over and over. Reliability is still a challenge. So, okay, we've built this powerful, aligned, goal-seeking AI. Awesome. But for a while, it remained way too huge and expensive for most individuals or smaller companies to actually run themselves.
Right, locked up in big tech clouds mostly.
Exactly. So the next three concepts we need to touch on really solve this accessibility and cost problem, made it more democratic.
This is what some people call the efficiency triad. LoRA, MoE, and quantization. Basically, making giant AI cheaper, faster, and much easier to deploy. Let's start with LoRA low-rank adaptation.
Okay, LoRA. Think of the massive base AI model as like a giant, expertly pre-trained symphony orchestra.
Okay,
So-
orchestra.
Now, if you wanted that orchestra to learn a completely new style, say experimental jazz, the old wayful fine-tuning was like retraining every single musician on every single instrument.
Hugely expensive, massive amounts of data, time, storage.
Prohibitively expensive, yeah. And you'd end up with a whole new giant orchestra file. LoRA completely sidesteps this.
Cool.
LoRA says, keep 99% of the original orchestra musicians frozen. Don't touch them. Just add a few small, new specialized pieces. Think like adding a dedicated jazz conductor and maybe a specific drummer. Then you only train those tiny new adapter layers to learn the jazz style.
So you end up with just the original massive model plus this tiny little instruction file that tells it how to play jazz when needed.
Precisely. It allows you to fine-tune a huge model, often using just a single consumer GPU, and the resulting adapter file might only be, say, 100 megabytes instead of hundreds of gigabytes.
That's why the open source community exploded with custom models, right?
Yeah.
Specialization became cheap and portable.
Totally. Okay, next up, MoE, mixture of experts, popularized by models like Google's Switch Transformer and Mixtral. This tackles the speed problem of running these enormous models.
Right. How can a model with maybe 1 trillion parameters run fast?
It's a really clever architectural trick. Imagine the AI model is now a massive hospital staffed with like 1,000 different medical specialists.
Okay, hospital analogy.
In the old dense model architecture, every time any patient came in, even with just a common cold, all 1,000 specialist doctors had to consult on the case. A huge waste of expert time.
Right. Makes sense. The MoE approach is different.
Yeah. With MoE, there's a quick router at the front desk. When a patient or a query comes in talking about, say, programming, the router sends them only to the programming expert wing of the hospital. Only that relevant small set of specialists gets activated.
So companies can build these models with trillions of parameters, making them incredibly knowledgeable across many domains.
Yes.
But for any single question, they only actually run a small fraction of those parameters. Maybe just the relevant expert.
That's exactly it. So we went from building one massive general practitioner brain that had to read every textbook for every patient to building a huge team of specialists, but only calling in the one needed for the job. That's how they stay fast despite the enormous total size.
Clever. Okay, and the third part of the efficiency triad, quantization.
Quantization, the memory hack.
This is basically saving memory by using less precise numbers, right? Like rounding.
Pretty much. It's a pure engineering optimization. AI model weights, the parameters, are often stored as very precise numbers, like 16-bit floating point numbers. Quantization is like saying, okay, instead of storing pi as 3.14159265, let's just store it as 3.14.
It's good enough for the calculation.
Often, yes. For many models, reducing the precision maybe down to 8-bit integers until at 8 or even 4-bit cuts the memory requirement roughly in half or even more without a major drop in performance quality.
And this is what allows huge models like Meta's Llama 3 to potentially run not just on giant server farms, but maybe on a high-end gaming PC or eventually even your smartphone.
That's the goal. It bridges the gap between AI being purely a cloud or corporate asset and becoming a truly personal, locally runnable tool. Huge implications.
Okay, so we have the engine, it's efficient, it's connected. What's the last piece?
The last really critical concept addresses the final hurdle for agents to really take off and work together seamlessly, the need for a common language or standard.
Right, the Model Context Protocol, or
Yeah,
MCP.
yeah, MCP. This aims to solve what developers call the N by M problem.
Yeah.
Imagine you have 100 different AI models or agents,
Okay.
and you have maybe 1,000 different digital tools you want them to use, Notion, Slack, Google Calendar, Salesforce, whatever.
Right now, you'd have to write custom code, like specific glue, to connect every single model to every single tool. That's
So,
100 times 1,000, 100,000 custom connections.
a completely unsustainable integration nightmare.
Exactly.
MCP wants to be like the universal USB standard for AI tools.
One plug to rule them all.
Kind of. Tool developers just implement one standard MCP server interface for their tool. Then any AI agent that understands the MCP standard can instantly plug in and use that tool, no custom code needed.
That seems absolutely critical if we want agents to eventually manage our whole digital life smoothly.
It's fundamental for realizing the true potential of interconnected AI agents. Hashtag tech recap and outro.
So let's just quickly recap the journey we took through these foundational concepts from the source material. It's quite a story. We started with the core engine, the breakthrough idea of attention and the transformer architecture.
Yep, built the engine. Then we scaled that engine way up with models like GPT-3, unlocking few-shot learning, the ability to instruct AI with prompts, not just program it with data.
Right. Then we realized raw power wasn't enough. We needed alignment. We taught the AI to be helpful and safe using human preferences through techniques like RLHF.
Made it useful. And then we connected that aligned brain to the live dynamic world, using RG to give it access to real-time data safely, and empowering it to actually act on goals using the agent framework.
And finally, the efficiency revolution, making all this incredible power accessible, affordable, and fast enough for widespread use through clever engineering like LoRA, MOE, and quantization.
Made it practical.
Yeah. The field moves incredibly fast, it feels like it sometimes, but when you break it down like this, these core building blocks, they're actually quite understandable.
You really are. And what's truly fascinating now, building on that last point about MCP, the common language, is that the next big frontier might not just be about smarter algorithms or bigger models. It's shifting towards better governance and better standards.
Right. That MCP idea raises a huge question for the future, doesn't it?
It really does. As these agents, using protocols like MCP, gain the ability to plug into and potentially manage everything, your email, your bank accounts, your work calendar, your smart home, how are we as a society going to solve the immense security challenges, the liability questions, the need for industry consensus to make this safe and reliable for mass adoption?
That's the big one to think about.
That's really the challenge for all of us, for you listening, to consider as you watch this space evolve incredibly rapidly over the next few years. It's going to be quite a ride. Thanks for diving deep into the sources with us today.